Hey guys, welcome back to your favorite channel, Subhra the Geek. I am your host, I am your host, Subhra. So today we are back with our statistics video, another statistics video, on our third video of statistics series. Today we'll be learning about data tendencies. So guys, to stay updated, this kind of series which we have planned is catered to the industry. So you don't need to search for a lot of things throughout the industry, but to search for individual things and to minute details, we have gathered the data and we are presenting it to you. I, along with my very good friend Debayan, have designed this kind of series for you guys. So guys, please enjoy. For all the updates, what you need to do is please hit the subscribe button and the bell notification icon beside it so that you get updated each and every time we post a new video. If you like the video, please give a thumbs up. Please share it with your friends whom you think will benefit from this video. Guys, I am your host Shubro. Along with me is...
Debayan.
Let's start, shall we? So, Debayan, today we are going to talk about data tendencies. As I and you know, this is a very important topic while we deal with a large amount of data, real life data. So, Debayan, please give them an overview, then we can start.
So we're going to talk about three important aspects when we're talking about data tendencies or data centralities. We're going to talk about measures of centrality, measures of central tendency. Then we're going to talk about measures of spread, of dispersion in data, and then we're going to talk about how do we scale data and make them more robust to outliers or anomalous data when we're talking about features and data engineering and stuff.
So, guys, you have got an overview. So, next will be Debayan, who will be talking about each and everything in minute details. So, let's
Mhm.
start. Yeah.
So for the very first topic, we're going to talk about um, measures or metrics in statistics that talk about how the data is clustered or grouped together, or how the data tends to some place, tends to a certain point, right? So we are talking about, you have a set of data, you have numbers over here, right? So what we are talking about when we talk about central tendency is those values, x1, x2, x3, x4, dot 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 xn, to tends towards a certain value, or get or have a tendency to get close to a certain value, right? What is that value? You can have three main metrics or measures of central tendency over here, and I think you must have heard of them in your high school or in your university studies. We have the mean. So this is the normal arithmetic mean average that you all know about. I don't think I need to explain to you what an average is. Then we have median, right? If you want a very quick quick summary of what do you mean by median, right? So a quick way to understand what median is that you sort this array in ascending order, and then find a number which comes right in the middle of that list, right? So you sort it, and then you find the middle number over here, and that is your median of that number set, of that list of numbers. And then you have a mode, right? This is the third type, this is the third measure of central tendency. A mode is a number in this list which has the highest frequency, right? So what you do is that you count the number of times a single number or a range of numbers appears in this list, and then you see which number comes is very common, which number has the highest number of repetitions, right? So the number with the max repetitions is the mode. So before we proceed any further on talking about these three, we need to understand certain things. When your measures, let's say of the central tendencies, are calculated from a sample, if you don't know what a sample is basically a subset of a larger data set or a collection of data. You do not always work with the larger data set, you always work with a smaller sample, with a small subset of that, of the real data set. and which you call the sample. So when your measures of central tendency, for example, there are other measures as well, we will talk about them later on. So when your mean, median, mode, right, these are the measures, and when when you calculate them, when you compute these three from a sample data set, from a smaller data set, they are called sample statistics, right? They are what you would call point estimate to real values, right? So when you have a sample, right, when you have a sample, so mean is represented like this, right? And when you have a sample statistic like a mean of a sample, right, these are point estimate, these are point estimates. It means that we do not know what the actual value is. You can only say that there is a possibility that this value is close to the actual mean. And when we say actual mean, it is the actual population mean, or the actual median, population median, or the population mode. You do not have these values. So these are point estimates to the real values, which can, only be obtained from a population, and which are not usually feasible to record or collect. You're not going to get data from everywhere, or all the data that is possibly available, so you always have to work with what you got. And so that's that. And you might have seen that, like, the way that we write about the sample statistics and population statistics is we generally use Latin characters, or English characters for point estimates, or from sample. So for sample statistics, you always work with Latin characters, right? So you see any Latin characters in statistics, this is a sample statistic kind of measure, or something computed from a sample data set. And if you are using population statistics, right, the real values, the real stuff. So when you're working with these guys, so you always use some Greek values. Now, for example, for median, we use this, and for the population statistics, you use this,
I think you mean mean.
right? So this is the population statistic. This is a mean, right?
Yeah.
So when you're talking about mean of a population, you use the Greek symbol mu. When you're talking about mean of a sample, right, or use the mean statistic of a sample, then you use this character x bar, right? This is just an example. Moving on, let's talk about spread. Let's talk about how dispersed the data is. In the previous one, we talked about how the data tends to cluster towards something, tends to move towards something. Here we're going to talk about how spread out the data is. And when I say spread, I literally mean spread, right? So if you plot it like this, you're going to have data points like this. So there's a sense of spread, right? It's spread across the space, right? It's spread out across the space. So this is what we're talking about. How spread out is the data? So what kind of measures, or what kind of metrics do we have that can allow us to understand how spread out, how diverse, how how distributed the data is, right? So we have something called range. I think it's very easy to understand. What is range, right? So you just take a mean, the minimum value, and a maximum value of the range, right? So you have something on mean over here, or maybe a max over around over here, right? So that would be your mean or max. This is also a statistic of a measure of spread, right? Measure of spread. You have variance. You have something called variance. So what do you mean by variance? Simple term, a variance is defined as an average square deviation from mean for a given list of numbers, right? So what do we mean by that? So average squared deviation from mean, right? So if you have a sample, right, you take every number from it, you subtract it from the sample mean, right? And then what you do, you take a square of it, you take a sum of it, and then you divide it by the number of samples, number of observations, number of data points in that sample. This is going to be your variance. There's also another thing called standard deviation, very common, commonly taught in high school, right? So what do you mean by standard deviation? Standard deviation is just the average deviation from mean. So the variance was average squared deviation, and standard deviation is average deviation. And the way you compute standard deviation is directly from variance by just doing a square root of it, right? So what you do is that you just square root of it, right? So the symbol that we use for standard deviation is sigma. Yeah, this is a Greek letter sigma, and variance we use sigma square. Simple enough. There, so variance is a square number. The square root to get a standard deviation, and the standard deviation is measured by a symbol called sigma, and the variance will be sigma squared accordingly. Three possible measures of spread we can use. There's also another one which you might have forgotten, like if you don't remember it. It's called interquartile range, or the IQR. Very important, please note this down. So the way that you work with interquartile range is that you have again that list of numbers that we talked about. You sort your list of numbers in ascending order, right? So sort it out in ascending order. You sort it out in ascending order, right? So then mark 4 points in that list, right? So you mark 25, 50, 75, 100% in that list. What do you mean by that? So when you sort it, right? So right around this point is a 25%. Right around this point is a 50% of your list. Right around this point is a 70% of your list. And right around this one is a 100% of your list. Obviously, this will be 0%. Right? So this is your list, right? What you did is you drew some markers over here, right? So these are your ranges. These are your quartiles, so to speak. This is your 25th quartile, your 50th quartile, this is your 75th quartile, and this is your full data set, or your 100 quartile. And the IQR is defined as the number of data points, or the number of values, or the number of elements that you get between 25% and 75% marker, right? So let me share this down. This region, right? This region, or the values that lie in this part of the list, or the set of numbers, is called, the number of data points is called IQR. This is the IQR, right? So IQR is a very good measure of spread, and this is much better than these simple ones like range or variance, because it does not rely on any endpoint to, so to speak, right? So in your range, you depend on your extremities, right? So let's say you have a list like 0, 1, 1, 3, and suddenly 100 number. This seems out of place, right? Wouldn't you say that this guy seems out of place, right? So if you take a range of this, your range would be, minimum would be 0, maximum will be 100. That is technically correct, but that is not exactly a very good measure of spread, because your measure of spread should be between 0 and 3, or around that number, right? So interquartile range will not be affected by this, because 100 lies way beyond any other 100%, and we're talking about 25 to 75% only, which is where 0 and 3, 0, 1, 1, 3 will lie. So IQR is much more robust in that sense, and it does not get affected by outliers, which can contain wrong values of range and variance. It can screw up the whole metric, right? And while we're talking about when we're talking about robustness and these kind of things, let's talk about it. Let's talk about robustness. What do I mean by robustness, right? So robustness is basically, it's like a measure, right? Well, a measure that cannot be affected by outliers or abnormal data, right? So a robust, when we're talking about robust something, robust metric, robust evaluation in machine learning or data science, this is what we mean. A robust measure, right, is something not affected by outliers. Clear this, be very clear about this. A robust measure is not affected by any kind of outliers or abnormal data, right? And so you would always want to choose some metric or some value, or some form of evaluation criteria for your model, for your process, for your algorithm, which is not affected by edge cases, boundary cases as we call them, or which can break your code, right? So keeping what we have learned in mind what we have learned today, median would be a more robust measure of central tendency than mean, right? So median would be a more robust measure than mean for central tendency, and IQR would be a more robust measure than standard deviation. And standard deviation, comparatively speaking, would be a more robust measure of dispersion or spread than simple range, right? So if you have a chance to work with median and IQR, please do so. That's always better, and you would be at least confident that your data is not influenced by any kind of abnormalities in the data itself.
Exactly.
The last topic of today's video is scaling, right? If you have already ventured into the world of data science and machine learning, you have done certain experiments, if you have done certain coding problems, so to speak, you must have heard of something called feature scaling or feature normalization, feature standardization, right? So what do we mean by this? So data scaling, right, or feature scaling, the same word. We're going to talk about more about features in the next video, in upcoming video. So data scaling in is in essence a form of transformation, right? So what you're doing is that you have a data point, right? So you have a data point, let's say d, right? You apply it on a function, right? A function that applies on d, right? And it changes it to something else, right? It was almost like a ratio. Think of it like a ratio, like a percentage or something. It's a form of transformation on a data point such that it becomes a new data point. And the property is that this data point is always within a range, right? Which is called the domain of that function of the transformation, like in set theory and function theory. Um, so this range is what is useful for us, right? Let me give you an example, right? So when you have a data set, when you have a very large data set, right, and you have so many columns or variables, so to speak, it's a multivariate data set, right? So let's say there are three variables, right? So v1 has a range like 0 to 100, v2 has a range from 25 to 75, and u3 has a range from 1000 to 3000. You can go about your statistics, you can go about your fancy algorithms and stuff like that, but you can expect that there will be some sort of problems when you're trying to perform any kind of optimization algorithms, any kind of machine learning or deep learning kind of algorithms on this kind of data set. And the reason is why is because they all operate at so many different ranges, and they are so spread out in that aspect, in their own range, in their own spread, that it's very difficult for the model to sort of understand how they are correlated with each other. It becomes very difficult for the model to do that. So what you do is that you apply some kind of transformation functions, and you make sure that all of those variables have some sort of commonality in the range that they're in. You basically apply some kind of ratio or proportionality constant between them, and make sure them all of them are between 0 and 1, 0 and 1, and this one becomes like minus 1 to 1. It's very small, right? You convert it, the range, you convert it in proportionality, the ratio is very small, the range of values is very small, it becomes a very manageable range, right? And it's very convenient to operate in. Deep learning and machine learning models find it very easier to work with when the range is very small, and it's easier to model in general, in practice, right? There's a third important reason why scaling is important, and I think people always miss this fact. And this is, scaling makes relationships between variables. Please remember the very first lecture in our statistics course, we talked about relationships between variables, right? So scaling makes those relationships between variables more linear in nature, right? And when I say linear, I mean there is some sort of like subtraction, some sort of in a formation like this, it becomes some sort of equation or some sort of relationship that is very close to the linear equation, some sort of linear relationship. Linear relationships are always easy to understand and work with. It's very easy to understand, okay, yeah, there's a proportionality constant, this is based on your intercept, and this is effectively a slope and your gradient, right? And your variables are directly connected like this. So it's very easy to work with linear models than non-linear models, where sin x, cos x, and all those comes, and combinations and all those comes. So it's always beneficial to understand where you have to apply scaling, and please do so whenever it is possible for your case. One last example before you go, right? So although this is not a part of this topic, I just want to give you a clue where you find this useful, right? So when we will
Devan,
be
can you
talking
zoom in
about,
a bit?
yeah, sure, sure. So whenever we are talking about, when we will talk about machine learning and algorithms, about specifically the gradient descent, right? You would find this kind of diagrams. Obviously, no need to understand. There is no need to panic about, you do not understand these things. But look at how the data, look at how the circles, right? These are concentric circles. These are where the data points are, and we are trying to perform an optimization. We are trying to find the minimum value for a function, which is, we'll talk about that later on. And reaching the center is the goal of the algorithm, so to speak. The goal of all machine learning algorithms is to find the minimum point where it's most stable, right? So you can see that if you do not scale, if your two variables, two input variables, are totally out of range, so it's very difficult to work in like in this kind of range. So one is spread out in this direction, and one has a very small range like this. It's very difficult for the model to work in this kind of thing. But if you do scale, right, and you keep it in the 0 1 in a range, it becomes very equidistant from each other, and it's much more easier to fast travel over here, right? So if you have random starting points to start, what is the probability that how much time will you take from here to here? It's all varied, right? So if you scale, it becomes more like, this is just a scale thing, but it's highly likely that all of them become equidistant to work with, and it's much easier to find that minimum value. If you do not understand this part, don't worry about it. We'll talk about it detail in upcoming courses. But plus this is a real life example where scaling actually helps, and people really recommend using scaling in every aspect of machine learning and data science.
So I think that would be all for the day, Debayan.
Yeah, yeah.
Yeah. So, guys, we have learned a lot from Debayan regarding the data tendencies today. Starting
Mm-hmm.
from measure of central tendencies, then we went on to mean median. First, we learned about mean median mode, then we learned about range, interquartile range, then variance, standard deviation, that's dispersion of data. Then we talked about robustness of data, and finally,
Mm-hmm.
we talked about scaling of data. So, guys,
Mm-hmm.
you have got a very good idea about what we have learned today and how to apply them to your model so that you get your result faster and to the accuracy which you want. So, guys, that would be all for the day from our end. If you have any queries regarding any part of the course, we have our Discord server, exclusive Discord server ready for you guys so that you can communicate with us anytime, where I and Deban will try to help you out throughout the course and throughout any time where we can help. Will be always there. The link is in the description box. So, guys, these videos are like what we are doing is completely our effort, and to help us, what you can do is give us a subscribe, share this with your friends as much as you can, and give us a like also. So, guys, that would be all from our end. It was your host Shubro along with
The Bayan.
signing off. Bye bye.